Media. So, Doctor, the floor is yours.
Thank you very much. You are very kind. So, birefringent is everywhere. We can find it in really important device like optical fibers or really interesting medium like vacuum, but also in screens or in our skin. And again, we can find it in really different materials like polymers or minerals. So birefringent is everywhere, but there is a huge problem in how we understand birefringence and how we measure it. So we will talk about that and how we solve this problem. But first, let me introduce myself. My name is Camilo and I am a Colombian guy. So as a Colombian, I really like to see Colombian people around the world like Sofia Vergara, and she interprets a character, and its character has some problems with the English, and she has struggles in communication. And I feel a little bit like Sofia Vergara right here because my English is not so good. But I promise you that I have really good arguments to convince you about the relevance of this problem. So let's talk about physics. When we talk about birefringence, we first need to talk about electromagnetic waves. So an electromagnetic wave is composed by two parts, the electric field and the magnetic field. So when we just look the electric field, we could see that this field describes some shapes when it propagates. Here we have linear shapes and here we have circular shapes. And those shapes is what we call polarization. So polarization, the polarization of light is in general described by an ellipse. So as an ellipse, it is perfectly described by two angles, the ellipticity and the orientation of the ellipse. But also polarization is described by stock parameters. And those parameters, we could measure it in the lab, but also we could strategically describe by those angles, the angle alpha and chi that define the ellipses. So if we want to describe polarization easily, we have to use a configuration space. And this space is what we call Poincare sphere. This sphere, each point of this sphere represent a different type of polarization. There are they are all the polarization state that we could find in nature. So what is birefringence? Birefringence in terms of Poincare sphere is just a rotation around an arbitrary axis, a rotation that is defined by two quantities, two parameters that we will talk about that later. And this parameter define the axis of the rotation, and the angle of rotation is this parameter gamma. So they are what we call intrinsic parameters. Intrinsic parameters are elliptical retardation, and eigenmodes. So those are intrinsic parameters. But in polarization, in birefringence, there are many important properties, and we will discuss this one. This paper was published in 1941 by Professor Jones and Professor Horwitz, and they describe three general equivalence theorems. So those theorems define what we will call equivalent parameters. So a rotation or a birefringence, an elliptical birefringence, could be defined in terms of two more simple birefringence, a linear birefringence and a circular birefringence. We call this one elliptical birefringence because the axis is defined in an elliptical state. Those states right here are elliptical. The linear state are right here in the equator of the Poincare sphere, and the circular state are in the pole of Poincare sphere. So An elliptical rotation, a rotation around an arbitrary axis in Poincare sphere, could be decomposed in terms of two more simple rotation. Uh, so let's take a look of this example. We have this elliptical birefringent, and we could decompose. We have this incident state right here and the emergent state here. So we want to go from this state to this state, but not by this rotation. We have to use two steps. So first we begin with this state, and we rotate an angle phi around the axis S3, and we find this state. So from this state, we could define an axis right here, and we could rotate the red state to the emergent state right here. So we have three different parameters, the equivalent parameters. The retardation here, phi, the axis that is perfectly defined by alpha prime, and the rotation delta. So the equivalent parameters are called optical activity, the rotation around S3 axis, the axis coordinate alpha prime, and the linear retardation delta. So if we look the mathematical relations between intrinsic and equivalent parameters, we will find a mathematical problem. So if we try to describe an elliptical birefringence in terms of matrices using Jones' theorem, we could describe it by a product of two matrices. So when we make the product and establish the relationships between equivalent and intrinsic parameters, we will find those three equations. But if we analyze the properties of those equations, we will find that they are non-bijective. So there is a problem, a mathematical problem here. So let's take a look. If we have three intrinsic parameters defined, we will find many different equivalent parameters. So it could be seen just a mathematical problem, but as we will see, this is a physical, real problem and really important for all the application that birefringent has. So let's talk about the physical meaning of equivalent parameters. First, we need to talk about law of linear birefringence. If we have a laser here and a polarimeter here, we could put a linear birefringent. If we have an incident state from here and we transform this incident state using this birefringent, we could find this in Poincare sphere. We could find the incident state that was transformed and become this emergent state. But if we take the linear birefringent and we rotate it, we won't find just one emergent state, but a curve of emergence states. So we want to find those emergent states because it's pretty useful for application. We want to find all the emergent states. So that was proof that this curve that looks really complicated is just the intersection between a cone and Poincare sphere. This cone is defined by this angle, the angle delta, the retardation of the linear birefringent. So what happens when we talk about elliptical birefringence? There is the same law. So if we take an elliptical birefringence and we rotate it, we will find a curve pretty similar, but it has some difference. So this is the curve of emergent state created by a linear birefringent. If we see the curve of emergent state created by an elliptical birefringent, we will find almost the same curve, but the emerging state is rotated. We find that the incident state is not the same, but they create the same curve. So this give us some ideas. We could use the first Jones theorem to trade this problem. So an elliptical birefringence could be defined in terms of linear birefringence and circular birefringence. So if we take the curve of emergent state, this curve could be right in terms of the curve of emergent state defined by a linear birefringence and a rotation around the axis S3. So it's like we take this cone in linear birefringence emergent curve and we rotate the cone. So this is the cone. And this is how we define the law of elliptical birefringence. And this law is fully defined by two parameters, the parameter phi and the parameter delta, that we called previously equivalent parameters. So equivalent parameters have some physical meaning. They are not just mathematical expression or a mathematical way to decompose the problem. So if we come back to the non-bijective problem, we will find something really interesting. If we have a researcher here in Colombia that wants to know the properties of a material, and they want to measure those properties, specifically the equivalent parameters, they could find some parameters that satisfy the equation, the parameter phi and the parameter delta, and he could reconstruct or create the shape of the emerging states. But if he talked to a colleague in Brazil, for example, and the colleague want to measure those properties, he could find other parameters and also other emergent state. So if we have a problems with non-bijective relations, we will have problems with all the possible emergent state. So this is a huge problem because we don't really know which states we will find. So this is the physical huge problem here. And this is not, I want to emphasize, this is not a mathematical problem. This is a problem that is relevant to all kind of application and all kind of science. So we have a problem. So we have to find a way to measure the specific equivalent parameter that has physical meaning and not the mathematical equivalent parameters. So we will discuss a comprehensive characterization of birefringent media, but we will talk about this in general terms, not in the mathematical boring terms. So first, we have to define two incident states, just two. An incident linear state right here and an incident circular state. And those states will be transformed by an arbitrary birefringent, and they will be the emergent linear state and the emergent elliptical state. So if we draw those states in Poincare sphere, we will find this. The incident circular state is right here, and the emergent elliptical state is right here. And the incident linear state is here, and the emergent linear state is here. Those states were transformed by an arbitrary birefringent. And this birefringent is defined by an axis and a retardation. So we want to find the axis and the retardation based on those four states. So let's rotate Poincare sphere for a while and analyze the problem. If we have those states, we could see that incident circular state and emergent elliptical state live in the same plane. So the same happens with linear state. If we find the difference between those incident circular state and emergent elliptical state and the linear state, we will see that those vectors live in the same plane. So living in the same plane, if we calculate the cross product and we normalize the cross product, we will find the axis that defined by refringence. So we will find eigenstates. So we will find elliptical retardation with this idea. In the lab, we know the incident and emergent state. So take an arbitrary incident state and an arbitrary emergent state. And we already know the axis. So if we take the incident state and we project them in the axis, we will find this vector, this red vector. And this projection is the same by the two incident or the emergent state. With this projection and this vector, we could find the vector Ri, and this vector and the other vector Re have an interesting relation. The angle between those vectors really or define the elliptical retardation gamma. So we could find gamma. But also we want to find the equivalent parameters that has physical meaning. So we have to use the curve of emergent state defined by the law of elliptical birefringence. This is the only way to ensure to not passes through the non-bijective problem. So if we have the incident linear state and we study the relationship between this incident linear state and their emergent linear state, we will find that they are related by the angle phi and the axis alpha prime. But also, if we study the incident circular state and the emergent elliptical state, we will see that this state and this state are related by the angle delta. So we could find those equivalent parameters. So with this idea, we could calculate the intrinsic parameters and the physical equivalent parameters. And with this, we could reconstruct all possible emergent states, something really important for application and for different areas in science. So the main contribution of this work is, first of all, define a physical interpretation for equivalent parameters, but also establish a new physical reliable measurement method. If you want to discuss the method, the data, the setup, or the implication of this work, you can write me an email right here. So that's all. Thank you very much.
Dr. Texter, that was a wonderful presentation. So now let's see if there's any question from the floor.
A wonderful presentation, and we have few questions for you from the audience. The first question is, what environmental factors like temperature or stress most affected your results?
Could you please repeat the question?
What environmental factors like temperature and stress has affected your results?
Okay, in the lab we have a stress control about the stress and the temperature. There are fixes. We don't change those variables because those variables change by refrigerants. So we have to ensure those quantities are fixed.
Okay, got it. And The next question is, which technique did you find best for measuring by reference in your samples and why?
Okay, we find that the the techniques, the actual techniques, the techniques nowadays have some problems with these non-bijective relations. So we create our own technique to measure by reference, and we are preparing an article to publish all this information.
Got it. And how do you see this work being used in practical applications in the industry?
Okay, I think we have really good device that works with birefringence, like in optics, quantum optics, photonics, or when we discuss the application, we talk about vacuum. We want to measure the birefringence of vacuum. So I think that those methodologies, those methods to measure birefringence could be really useful for those applications, for fundamental physics, but also for technology.
Wonderful. Thank you so much, Camilo, for your wonderful presentation. In fact, it was full of technical details. It was there more of physics. And yeah, I see a lot of potential in this talk. Thank you once again.
Thank you,
Thank you
David.
so much, Doctor, for that informative